Find the volume when the region x goes 0 to 2 and y goes from 0 to 3 root x squared plus 6x is spun around the line x equals -3. There are some options: 48 pi, 60 pi, 64 pi, 72 pi, 128 pi. Well, anyone want to take a guess?
64 pi.
64 pi is not a bad guess, actually. But it's not that. Well, I'll tell you, 64 pi was included as a good, we call these distractors in the business. So people, when they write multiple choice problems, there's this sort of notion of distractors. Answers that look really tempting. And so one of the things that happens is we know how students think. And you might say, well, how do you know that? Because we programmed you. We taught you. So we know how you think, but we also know what mistakes you make. And so because we know common mistakes, we'll say, aha, here's a common mistake. We'll throw that in. Now, why is 64 pi a good distractor? The answer is 128 pi. Well, how close is 64 pi to 128 pi? Yeah, 2 away. So if you forgot the 2, you would have gone 64 pi. All right, so be careful. Be careful. All right, so what do we do? Well, we have to figure out what we're after. Now, we know we're after a volume. There's only a handful of formulas for volume. We also know it's a volume where we're spinning. Okay, we're spinning around an axis. That means it's a volume of revolution. That narrows it down to 2 possibilities. Disk or shell, or I should say washer or shell. Now, which method? Well, you might be able to use either. I always say, well, let me go with the way the problem was presented. Here, the problem was presented using functions of x. So I say, well, let me slice with x. So I'll take thin slices that are vertical, up, down. So there's dx slices. And if I spin that around the line x equals -3, I would see that that shape is forming a shell. So I'm thinking shell method. All right, now I have my strategy in place. I pull out my shell method formula, and I start putting the pieces together. Well, my width is dx. I'm integrating with respect to x, because that's what the dx is telling me. And I say, well, x is going from 0 to 2, and I can see it right there, 0 to 2. I have my 2 pi. That's always just 2 pi. The radius, well, that's the distance from my slice to where I spin. So where I'm at is x. Where I'm spinning is at -3. So it's x subtract -3, or x plus 3. So that's the radius. Then the height is the distance between these two formulas. 3 squared root of x squared plus 6x. All right, so setting it up, that's half the battle. But how do you integrate? Well, we're going to talk more about square roots today. Square roots can be very unpleasant in some sense. So you have to be careful. So what do we do? Well, we look for a couple of things. It'd be really nice if there's a square on the inside. There's often not. So we start thinking of other things. And we say, well, I have a function, x squared plus 6x, inside another function. What is the right technique when you see function in function? Substitution. That should be one of the first things you should go and check. Say, if I see a function, is there a convenient substitution? Now, substitution, I like to say, it's an inside job. All right, look for the thing on the inside. Well, x squared plus 6x. Okay, let's try that. Take the derivative, be 2x plus 6. And now, if you look, that 2 times x plus 3. That's 2x plus 6. Almost like they planned it, because I did. And indeed, this line wasn't just random. It was a very special line. If I'd picked another line, hopeless, hopeless. But no, I chose one where we had hope. All right, so then the integral becomes 3 pi u to the 1/2 du. Now don't forget, when you do u substitution, update your bounds. These bounds here, 0 to 2, these are x bounds. So it's x equals 0, x equals 2. They're not just some random numbers, they have significance. When you're switching to u, you need to go from x's to u's everywhere, and that includes your bounds. So we want to have u equals something to u equals something. So how do you figure out the bounds? Well, you plug in. Plug in 0 into x squared plus 6x, out comes 0. Plug in 2 into x squared plus 6x, and out comes 16. So don't forget to update your bounds. All right, we integrate, because this is on our list of things we can integrate. We evaluate, and life is good. All right, any questions? I see a question.
In the step under the second, how did you get the 3 pi? Or how did that become 3 pi?
How did this become 3 pi?
Yeah.
Well, let's see what we accounted for. We have the x squared plus 6x, the square root. That becomes u to the 1/2. So far, so good? Good. Now, we need to get a 2x plus 6 dx. That becomes our du. All right. I should probably switch to a different color here. So, say, all right, how do we get that? Well, we have the dx, and then we have x plus 3. Well, x plus 3 is not quite 2x plus 6, but if I take the 2 times x plus 3, that is 2x plus 6. So that's the green part. Now, what hasn't been circled? The pi and the 3. So that becomes your 3 pi. So you get 3 pi, u to the 1/2 du. So that's where all the pieces are coming from. So everything gets accounted for. Anything else? All right, good. Well, on to our thought for the day. And this is a Japanese proverb, and I'm not even going to try. I don't speak Japanese, but I can tell you the translation. Even monkeys fall from trees. Now, what does this mean? Well, turns out monkeys are really good at trees. They're professionals. But there are monkeys that still fall down from trees. And the point of this proverb is to say, look, no matter how good you are, you'll still make mistakes. And so, as you're going through this class, no matter how good you are, you'll still make silly mistakes. I make them. You will catch me. And I appreciate you pointing out my errors. So feel free to say, Steve, I think you messed up. And you're right. Thanks for catching that. But you'll make them too. And I want you to be aware of that. Now, there's a couple things that means. One, if you realize that mistakes are possible, it gets you to learn to check your work. And oftentimes, it's easy to catch a mistake early, so to save yourself a lot of heartache. So get in the process of double checking as you go through. The other thing is, don't beat yourself up too much. Sometimes you make some mistakes, they're small mistakes, and you start saying, well, this just isn't for me. I'm never going to be a professional Calc 2 person. No, have faith in yourself. Everybody makes mistakes. You can be that professional Calc 2 person. So, all right, that's today's thought. All right. Well, what we have for our agenda for today? We're going to do a few more practice problems with volume because I like these problems. And then we're going to get into arc length. Now, when we talk about arc length, we're going to talk about arc length 3 times this semester. So this is day 1 of arc length. We really love it. And so there's going to be arc length in different settings. Our setting for today is the y equals f of x version. If you're looking in the formula sheet, this is where we're at today, that version of arc length. So we're going to look at showing why does the arc length for y equals f of x look like the integral from a to b square root of 1 plus f prime of x squared. And in particular, it's like, square roots. Oh my gosh, really? Yes?
That looks like arctangent. Doesn't it square root of 1 plus x squared?
No, arctangent would be 1 over 1 plus something squared. But this. Well, dealing with square roots, we're going to learn a lot about how to deal with square roots this semester. Okay. So, practice with volume. Find 2 pi, integral 0 to 1 of x arctangent of x dx. Now, I said practice with volume. What do you notice is not written in that problem? Volume is not written in that problem. So you're like, wait, how in the world are we supposed to do a volume problem when it doesn't say anything about volume? And indeed, all it says is find this integral, and it doesn't look like we have the tools to do this. Well, not yet. Give us a month, and we will. But that's a month. Okay, so what can we do? So here's what we can do. We can say, look, we're presented an integral. Somebody has handed an integral to us. And we say, all right, let's interpret it. We can interpret this integral. So is there anything about this integral that might make us think of volume? The 2 pi. 2 pi in the front there says, hey, we have a formula that involves 2 pi. Now, the integral of x arctangent x, it doesn't need a 2 pi there, so that 2 pi is very suspicious. So I say, okay, there's a 2 pi. Let's think about what that 2 pi is. What is a formula that involves 2 pi? Shell method. Okay, so let's recall our shell method. So we have that volume is the integral a to b 2 pi radius, height, and width. So with this in mind, we can say, well, it looks like we could piece together from this integral, we could assign pieces here, and then we could probably figure out what this corresponds with, at least one interpretation of this. So looking at this, what makes a good candidate for width? Dx. So, okay, we can say, well, let's think of this as our width. What makes a good candidate for radius? X. All right, let's think of that as our radius. And how about for our height? Yeah, arctangent. Arctangent is a terrible candidate for radius. You know, because radius should look like a distance to some line. Arctangent x doesn't look at all like that. Okay, so given that this is the case, we say, okay, now we can draw a picture. So we have the function arctangent, of course, everybody's favorite function. We all know it by heart. And we only need to go from 0 to 1. Arctangent of 0 is 0. And let's say this is 1, arctangent of 1. You have that memorized? Arctangent 1? What? Pi over 4! Ah, beautiful number. Okay, so it's doing that. Okay, so here is our region. All right, so we have our y equals arctangent of x. We're going from 0 to 1. We'll shade our region in. Okay. Now, we're integrating with respect to x. That means we're taking currently our vertical slices. our distance to where we're spinning around is x. Where are we spinning around? So what is x away? So if I'm at, think of this, this is my slice at x. What is x away from me? The y-axis. So we are spinning around the y-axis. So we're piecing together. We say, all right, given that we have our radius, width, and height, our arc tangent gives us, in our bounds, that tells us our region. And then we figure out from our radius where we're spinning around. So we say, okay, great. So now we have sort of a setup. We say, we're finding this volume when we spin. All right. Now, you might say, cool, but how does that help us get our answer? Well, it's allowed us to interpret what we're after. We're after a particular volume. So volume from spinning our region around the y-axis. Now, that's if we use shell method. Let's think about it. Do we have a different way we could compute this volume? Washer method. So if we did the washer method, how would we be slicing? We could slice now horizontally. Okay, so let's think about washer method. Well, volume, integral a to b, pi, and then we have our big radius, quantity squared, minus our little radius, quantity squared, and our width. Okay, so, and we forgot to mark, this is at pi over 4. So let's figure out what this is in terms of washer. So let's set up our integral. What's our width going to be? It's our dy. So we have our pi. We're going to have something squared minus something squared dy. What will our bounds be? Zero to pi over 4. Because we're integrating with respect to y. That's our dy, so we have to say, well, where does y start? We start at the bottom, which is at 0, and the top of the region in terms of y is at pi over 4. Now, what is our big radius? So our big radius is from where we're spinning to the curve further out. What's that length? It is the 1. 1 minus 0. All right, almost there. Now, inner radius. Well, we go to the curve. Our curve is y equals arctangent of x, but that's the wrong way to write the curve. We need to re-express this as x equals something of y. If y equals arctangent of x, then x equals tangent of y. Why is that true? Because arctangent is the inverse function of tangent. Okay, so what's our small radius? Tangent of y. All right, good. We've made some progress. And this looks slightly more, I don't know if palatable is the right word, but at least it seems possible. The original one seemed like, ugh, really? But this one's like, yeah, maybe. Okay, so we look in our formula sheet and our integrals, and we say, aha, the integral of tangent squared of y is... So we grab our formula sheet, tangent squared of y, tangent squared of y, tangent squared of y, tangent squared of y. It's not there. No! So we were so close. We were so close. But wait a second. Does tangent squared show up anywhere? As your eyes drift north, there is a tangent squared. Now, what is that tangent squared telling us? Well, this formula is very handy. We're going to rely on it quite a bit later in the semester, so we might as well learn about it now. It basically says, if I have a tangent squared, it's like I have a secant squared. I can more or less swap them. Now, more or less says tangent squared is not exactly secant squared, but close. So what is tangent squared? Secant squared, move the 1 across, secant squared minus 1. So if we replace this tangent squared by a secant squared minus 1, and we carefully keep track of our signs, we get that this is the same as pi, integral 0 to pi over 4, 1 subtract minus 1, 2, and minus secant squared y. All right, now can we integrate secant squared? Back to the formula sheet. Does it show up anywhere? The derivative of tangent is secant squared. So the integral of secant squared is tangent. Now, hopefully you'll just know it, but if not, that's how you can look things up. Okay, so that says we can integrate the secant squared. Can we integrate 2? Yes? All right, so we get 2y subtract tangent of y. And we're almost done. Plug in 0 to pi over 4. Plug in pi over 4. 2 times pi over 4, also known as pi over 2. Tangent of pi over 4. And you probably say, Steve, you just told us monkeys fall down from trees. You forgot your pi. All right. So there's another pi there. Tangent of pi over 4. 1. And then there's, don't forget to multiply by pi. Plug in 0. 2 times 0. 0. Tangent of 0. 0. So we end up with 1/2 pi squared minus pi. And we did it. Woohoo! Nice. So this is the power of saying, hey, I have an integral. I can think about what does it represent. And sometimes knowing what it represents can help us figure out how to integrate it. Now, as I said, we'll have tools that we don't have to resort to volume, but we don't have those tools yet. All right, any questions?
Can you please explain in shell formula, when we have this radius, is it radius like of what? Because when we have different shells, radius changes, right?
So what's the radius? It's the radius of, so the question is, given shell method, what does the radius represent?
Yeah.
And the radius represents the distance from your slice to where you're spinning. So normally, if we're slicing with respect to x, our radius looks like x minus where we spin our spinning location. Or it could be where we're spinning subtract x, just depends on our relationship to where we're at, whether we're spinning, where we spin is to our left or whether we spin is to our right. But more or less it should look like x minus something. And so the punchline is it's the distance from where we're spinning. Now, our piece here looked like x, so our piece looked like x minus 0. So I said, oh, this looks like the formula for radius from x to 0. So that says spin around x equals 0, which is the y-axis. The radius can't be constant, no. It has to change because your slice location changes. So it has to look like x minus something or something minus x. I see another hand.
How did you decide not to use the shell method?
Well, so we did use the shell method to give an interpretation. But the thing is that if we use the shell method, we have to find a way to integrate x arctangent of x. We don't have that technology, but we will. So we did use the shell method to give an interpretation, and I said, let's reinterpret it using a different method. So we can come back in a month and redo this problem and say, who needs this? And after we redo it in a month, you'll say, let's go back to the volume way. I like that. That was a lot more fun. But spoilers. Anything else? Okay. All right. How are we doing on time? Well, should we do one more with volume? Or are you good with volume? You're good with volume. Okay, we'll skip that one then. Okay, so on to today's topic. So, we want to find the length of a curve. Now, when we're trying to find something, a total using integration, we start by saying, well, what's something we can handle? Now, something that we can handle is a straight line segment. We're really good at straight line segments. And because they're flat, we are really great at flat things. So you say, okay, if I have a line segment connecting 2 points, then what I can think of is it's part of a triangle where I have a change in x on one side of my triangle, a change in y on the other side, and then the length is that hypotenuse, and Pythagorean theorem, a squared plus b squared equals c squared. That lets me find the length of a line segment. Great. Life is good. So flat things, life is easy. Well, our goal is to say, but what if you don't have a flat thing? Maybe you have a curve. And in our case, we have y equals f of x. It's joining our endpoints. So we're going from a to b. So we have our a comma f of a, our b comma f of b. But we're not in a straight line. We have things moving up and down. Now you might say, well, what can we do? We could imagine, we could just say, well, I have some line. I just want to pull it straight, and I could measure it. Now, I just used my budget for the semester. You know, the math program doesn't get very much money. So don't expect anything more interactive than that. But that's what we would, in theory, like to do. We'd like to say, well, let's make it straight. So we can't quite say, oh, let's take a piece of string and pull it taut. But we could say, well, let's sort of do something similar. So what we're going to do is to break things into small parts. When you break things into small parts, what happens is you can say, well, when I look close, even though it's curving, it doesn't curve much. Now, this is sort of how calculus, the heart of it works, is when you look nearby, things look flat. You zoom in. It's the same thing that we talked about when we talked about tangent lines. You zoom in on the curve looks flat, that's your tangent line. It's a flat thing. So we want to have that same philosophy. Say, okay, so let's take the curve, instead of treating it as a big object we're trying to pull straight, we'll chop it up into little tiny pieces. Now, each little tiny piece, it's not perfectly flat, but it's pretty close. Now, how can we make it even better? How can we make our approximation better? Smaller pieces. The more you zoom in, the smaller the pieces that you make, the flatter things are, the better the estimation. That's integration. zoom in, things behave nicely. Okay, so we're now going to focus on what happens as we go between 2 points. So here we have our first point. We'll call it at the ith point. So, x1, x2, x3, da, da, da. So here's xi and f of xi. And then the next one over, well, that's our xi plus 1, f of xi plus 1. And now the question is, what is the length of that line segment? Well, same thing we just talked about. We're just going to imagine that it's straight. It's a good approximation as things get better. So it's the change in x squared plus the change in y squared. Take the square root. Okay, well, what can we do? Well, what we're going to do, this may not be the most obvious thing, but imagine we want to pull this term out of the square root. So we're taking this xi plus 1 minus xi squared all the way out of the square root. So when you take the square root of something squared, it's just the thing. Well, technically it's the absolute value, but we've sorted this so it's the right sign. So you have your xi plus 1 minus xi. So that came from pulling out on the end. You grabbed everything from the first term, so that's why it's 1. And then from the second term, because we're pulling out, we actually have to add an xi plus 1 minus xi downstairs. Now, here's where we say, do you remember Calc 1? Oh, the good old days in Calc 1. Well, what do you have? You have a small change in y. Divide by a small change in x. Change in y over change in x. And they're very close to each other. So what are you doing? Well, you're approximating the slope of the line that's connecting those 2 points. So in other words, if you were just to say take these 2 points literally and just say what's the slope there, that's what this is. And because we're getting our pieces smaller and smaller, it's like you're zooming into the tangent line. So we're becoming the slope of the tangent line. In other words, the derivative. So we're becoming the square root of 1 plus f prime of x squared dx. So this expression right here, this is, you should think of this as the length of one piece. Really one very tiny piece. Well, okay, how do you get the total length? You add them up. And integration, whenever you see this integral sign, remember that says you add things up. So the integral from a to b will be the total length. And there's our formula for today. Any questions?
How could you move that piece from square root if it's a addition but not multiplication?
Well, when I remove it, I remove it out of both the terms, not just one term. So, how can I remove this? Well, I can't just remove it out of the first term. I have to remove it out of both terms. You say, well, how did you remove it out of the second term? That's where this piece came from. So everything worked properly. I didn't break any rules. So I'm following proper procedure. Okay, a couple of notes. We have here for y equals f of x. We could do x equals function of y. We didn't write that formula on the formula sheet because we're like, our students are good students. They're adaptable. They'll know how to change. The next thing, be really careful with square roots. It is never the case that the square root of a squared plus b squared is a plus b. But no matter how many times we tell our students that, they don't believe us. And on their quizzes and exams, they start writing that down. And I know it makes things work so nicely, but you get the wrong answers. So be careful. So usually when you see square roots, it means that there's more work to be done. So what's the work? Look for squares on the inside. Look for good substitutions to make. And sometimes the only thing we can do is set it up. So keep in mind, a lot of times when we do applications, it's just like, well, set it up, but that's as good as you can do for now. Here's another way you can think about what's going on. If you zoom in, here's our piece that we zoomed in. Our dx is our change in x, and our dy is f prime of x dx. And then if you just work through Pythagorean theorem, that's the piece that comes out. All right. Well, let's try a problem. So, this problem is so nice, they put it on exams twice. I don't think it's that fun, but okay, we can try it out. Find the length of the curve, y equals natural log of x minus 1/8 x squared, where x goes 1 to 3. Okay, well, let's make sure we learn how to recognize what type of problem we have. Is there anything about this problem that makes us think this is a length of curve problem? Anything at all? Yeah, it tells us length of curve. See, we start to pick up on these subtle clues. It's like, oh, length of curve. I should probably use a length of curve formula. And we also see what setting we're in, because we're given y as a function of x. So it's like, oh, it's a length of curve formula. Y is a function of x. So we say, hey, there's a formula. It looks like, length equals integral a to b square root 1 plus f prime of x squared dx. So we just have to identify certain things. What is the f of x? Right, this is your f of x. Now, is our formula telling us that we should go integral 1 to 3, square root of 1 plus natural log x minus 1/8 x squared dx? Or is there something else we need to do? Is this correct? No. What's wrong here? Yeah, you need the derivative. Don't forget the derivative. Okay, so what is the derivative of natural log x? 1 over x. What's the derivative of minus 1/8 x squared? 1/4 x. Okay, so we should have written down square root 1 plus 1 over x minus 1/4 x squared. Now, is this correct? Yes. And now we're off to the races. Okay, we just have to work this out. Okay, so what's going to be our first step, or what's a first step that we can do here to figure out what's going on? Yeah, we got a square here. Now, unfortunately, there's that 1 plus, so we can't just get rid of the square root yet. But what we can do is at least get rid of that square on the inside. We will expand. So, doing some algebra. Algebra. Okay, so as a reminder, a minus b quantity squared, a squared minus 2ab plus b squared. A plus b quantity squared is a squared plus 2ab plus b squared. These are things which are good to know. Not on the formula sheet, but nevertheless, good to know. Okay, so when we square this, we start with our a squared. What's that going to become? 1 over x squared. What will our minus, because there's a minus here, 2ab. So 2 1 over x, 1/4 x. I'll write out here this time. And our b squared? 1 over 16 x squared. All right. And we're going to follow good practice of always writing that dx on the end. They look for things like that. Now, in the middle, what does this term become? 2 times 1 over x times 1/4 x. It was a half, right? The 1 over x and the x cancel. 2 times the 4th is a half. Now, can we do anything? So currently this is 1 plus 1 over x squared minus a half plus 1 over 16x squared. So what can we do? It's like 1 minus a half, also known as plus a half. So we can combine. And you're like, well, that was nice while it lasted. But wait a second. Isn't it interesting how when we squared this part, we got 1 over x squared minus a half plus 1 over 16x squared. And now we have 1 over x squared plus a half plus 1 over 16x squared. Very similar. It's like the only thing that changed is that minus became a plus. Huh. Wonder if there's anything else that does that, where you just change one small thing and like the middle sign changes from like minus to plus. Anything at all that does that? What? What are you talking? Oh my gosh, it's right there. It's on the screen. Holy cow. Look, that minus is like a plus. What happened? Well, as soon as I have a minus there, there's a plus there. What? That's cool.
Discovery of mathematicians.
So this is like 1 over x plus 1/4 x squared. Wow. All right. Well, almost made it. That's okay. We still have space on the side. Okay, so what does this become? Well, now you have a square inside of a square root. What happens when you take a square root of a square? They cancel out. Now, do they really cancel out? There's a small technicality, but here they do. Here it's a yes. We'll come back to that at some point this semester. We'll have fun with that someday. All right, so integral 1 over 3, no square roots to be seen. 1 over x plus 1/4 x. What's the integral of 1 over x? Log x, good. Integral of 1/4 x. 1/8 x squared. And evaluate 1 to 3. Natural log of 3, also known as natural log of 3. Very good. 1/8 times 3 squared, 9/8. Subtract natural log of 1, also known as 0. And 1/8 times 1 squared is 1/8. We can make one more simplification here. 9/8 subtract 1/8, also known as 8/8 or 1. So log of 3 plus 1. And there we go. All right. Cool. Okay, let's do one other problem. We'll have time. Set up, but do not evaluate. Ah, the sweetest words in the Calc 2 language. The integral, or integrals, define the perimeter of the region bounded by the curves y equals cosine pi x, that's this red curve, and y equals 3x squared minus 6x plus 1, that's this green curve, and it even conveniently gave us the intersection points. What is the perimeter? So if you hear perimeter of circle, what do you think? Circumference, right? Our perimeter of a rectangle, it's the length of the sides. Perimeter is the length of your edge. So even though it doesn't say length, it uses perimeter, which is another way to express length. So it's like we learned to read the problem. Now, looking at this, how many integrals will we need? 2 integrals. Why will we need 2 integrals? We'll need one for the red piece, because that's one function, one for the green piece. That's the other function. So there are 2 functions that are making up this bounding curve. For each one, we need an integral involved. All right, which one do you want to do first? The parabola or the cosine?
Parabola.
All right. So notice we have the bounds, and we're going to use our x bounds because they're giving us x functions. So for the parabola, we go from 0 to 2, square root of 1 plus something squared dx. What goes in this piece? So we're doing the parabola. This is our f of x. What goes here? The derivative of f of x. What's our derivative? 6x minus 6. Now, what do we do for this integral after we've written that down? We leave it alone. We just have to set it up. We don't have to simplify it. We don't have to evaluate it. That's that. But we need to add the other piece. So now we're doing the cosine. Okay, now the parabola went from 0 to 2, but for the cosine, we're going to go from 0 to 2 as well. Formula square root of 1 plus something squared dx. What goes here? Oh, someone said negative pi. Excellent. Why was there a negative here? Derivative of cosine's negative sine. But it's not just negative. What else do we need? Pi. Why is there a pi? Chain rule. It's the best rule. It's a chain rule. Negative pi sine pi x. Quantity squared. Now what do you do?
That's it. Leave it.
Box it, and we call it a day.